Hello. Okay, so very good evening to all of you. Good evening. Good evening. So today, we are going to learn about ensemble methods. Ensemble methods. Good evening. Good evening. Good evening. Just wait here. I'm well. I'm well. So today we are going to learn about the ensemble technique. What are ensemble techniques? Certain time what happens, our data set is too large. Means here you think, this is my data set. My data sets are having ample of columns we are having. So you think there are various columns and we are having large number of rows. Okay, so think out a condition where we are having ample number of columns as well as ample number of large number of rows. It means my data set is very, very large. We can say it as a suppose I'm having my number of columns in hundreds and rows are also in lakhs. So if we give entire data to the model, so my model is not able to learn so much big data. Huge data means here I'm talking about the huge data. Huge data. So my model is not able to learn that data. Single model is not able to learn that data. So what we do in this case, we try to make the subset of the huge data set. So n number of subsets will be created. Subset 1, subset 2, subset 3, subset 4. So what will happen? Entire data set will be created in subset 1, subset 2, subset 3. We can create a subset n. There are a number of subset n number of subsets will be created. And those subsets are given to individual model learning. Those subsets are given to individual model learning. Okay. And when these individual model learning will learn this subset, the accuracy of all these different model will be combined and their final mean accuracy would be taken. The mean accuracy will be finalized accuracy. That would be what? That would be the final accuracy, mean accuracy. So the point is, in case of ensemble method, the entire data set is divided into subsets, and those subsets are given to the different models, and those models, their accuracies are combined, them find out the mean accuracy. Okay. Now the point is, see here. These single models are what? They are decision tree classifier. Decision tree classifier. These are individual decision tree classifier. And these decision tree classifier, I can take it 100, I can take it 200, I can take it 150, as many as till my results are okay. So the point is, ensemble techniques are those methods which are being worked whenever we are having a huge, large data sets. A single model is not able to learn that huge data set. So we divide the entire data set into subsets. Those subsets are given to individual model, which is a decision tree classifier individually, and their corresponding accuracy will be taken as the mean accuracy. Okay, so this is there. So here, ensemble method are divided into, ensemble methods are divided into two categories. Bagging, boosting. Okay, so in bagging technique, we create the parallel data sets. Bagging techniques create the parallel data set. In case of boosting, sequential data sets are created. Bagging technique is known as parallel technique. Boosting technique is known as a sequential techniques. In case of bagging, my data set is divided into n number of subsets. N number of subsets, like subset 1, subset 2, subset 3, subset 4, subset n. And these subsets are provided to individual models. So it means the entire data set is divided into parallel. And after dividing the data set in parallel, all the data are being learned by the model in parallel with the decision tree classifier. These all are DTC. So it means all are DTC. DTC means all the models are homogeneous. Homogeneous means all the models are same. They are DTC only. And their corresponding accuracy will be coming as the mean accuracy. This is a bagging. Now let's come to the sequential model, which we call the boosting technique. We are having a large data set. So if we are having a large data set, this large data set is being learned by one of the model M1. This model will boost out or amplify the learning and creates internally with this learning, it transfers its output to the second, it transfer its output as an input to the second model. So the data set is being learned by the model in sequential mode here. And then comes the final mean accuracy. So there, we do call it a sequential technique. So here we are having here certain algorithms which are going to work for ensemble methods, bagging and the boosting. For the bagging and the boosting, for the parallel method, there are certain models such as random forest, and one more is there when there is a huge data set is there. I'm talking about a very huge. So there one can go ahead with the extra trees. As the name suggests, random forest means a collection of trees. Same here, we are having a collection of trees, collection of decision trees. They could be into the form of 50 trees, 100 trees, 150 trees, 200 trees, it could be. So we are having a random forest, extra trees for the parallel bagging technique. Let's come to the boosting one. For that, we are having ADA boost. ADA boost algorithm, gradient boosting algo. They all are working. So random forest, extra trees for the parallel technique, ADA boost and gradient boosting for the sequential technique, boosting technique we can say. When we talk about random forest, ADA boost, gradient boosting, so we are having all type of algorithm here, such as in case of ensemble, they're talking about, suppose, random forest. So random forest is having its classifier and its regressor. Suppose I say ADA boost. ADA boost. So in ensemble method, we are having the corresponding classifier and we are having the regressor. If I'm talking about the gradient boosting, we are having a classifier and regressor. So the point is, or extra trees if I want to talk about, everyone is having its classifier and the regressor. So we are having all the regressor and the classifier whenever we are using this ensemble technique in case of very huge data sets. When our actual model fails, so there we can use the random forest, these ensemble techniques. So these are already present inside the sklearn. These all are already present inside the sklearn. Now, if I talk about certain more algos are there. So, but they are not a part of sklearn or anaconda. No. There are certain more algos also, but they behave like the same here. There's no difference here. Such as I say XG boost. This is just a boosting classifier or regressor. But again, this is not a part of anywhere in anaconda. If one needs it, so one needs to separately install it. There is one more like cat boost. But these are not a part of anywhere anaconda. They are completely separate libraries. So they are external libraries. So if one wants to take it here, so there are basically additional installation is required. But here we'll be talking about the anaconda. So here we are having random forest. But here, whenever we are talking about the ensemble here, random forest, extra trees, gradient boosting. So here we are having all the homogeneous models. Let's see the ensemble methods here. Ensemble learning is a machine learning paradigm where multiple models, we call those multiple model, which is a decision tree. We call it a weak learners because they are individual. They are trained to solve the same problem and combine to get better results. Bagging and boosting, two methods are there. Bagging often consider homogeneous weak learners. Homogeneous weak learners means here we are having a DTC. Decision tree classifiers we are having. That's why we are seeing it decision. Homogeneous means DTC we are having. All are same. So they learn them independently. Them means subset. So they learn them independently from each other in parallel and combines them following some kind of deterministic averaging process. So here they would be finding it out the mean accuracy. Now in boosting, here also it considers the homogeneous weak learner. So here also certain single type decision tree classifier, they learn the data sequentially in a very adaptive way and combines them with a deterministic strategy. So here we are having certain algorithm, which is bagging and the boosting here. Generally, when we talk here, generally our single classifier learns in this way. We are having a data set. A single model learns the entire data set. But when we talk about bagging, in case of bagging, the data set is divided, the entire data set is divided into chunks, subsets, and those subsets are being learned by the individual model, and their collection will be taken as the mean. Into the boosting, the data set is learned by one model and its output is taken as the input to the second model. In this way, the sequential techniques work to give the final results. So there are algorithms we are having. So here currently I'm taking the predefined files which had already worked here. So one can use any classifier, any classification files you can use them. So here, let me load out here iris data set I had loaded here. These are the earlier file which I had created earlier. These are the same file I'm using, but into the earlier file, I'm just adding some code only for the ensembles here. So the main one is here I'm loading from sklearn.dataset, import, load iris. Iris dataset is there, which is used for the classification purposes there. Okay, so there I reused it here. Other thing, your metrics will be same. Okay, your metrics here, accuracy, confusion, classification will be remain same. Only algo will work in the backend to give the highest accuracy. So here we are taking it here. I'm just loading the data set here. I'm splitting the data into the input and the output, making the train test split here. Now, here I'm coming to the algorithm. Inside the algorithm, I'm going to send input and output. Okay. So inside the input and output here, I'm going to use the bagging technique, which is a random forest. So here, just wait. Random forest is there. Inside the random forest, we are having both. Okay, we are having, see here, random forest classifier we are having. You can see here class sklearn.ensemble random forest classifier we are having. It will create certain trees inside it, trees. So when I talk about the trees, there are number of estimated trees are 100. N estimator is one of the parameter. Automatically, it takes 100 trees to learn the 100 subsets automatically. Okay. A random forest classifier, it is a meta estimator. Meta estimator means classifier that fits a number of decision tree classifier on various subsamples of the data set and uses averaging to improve the predictive accuracy. By default, it takes 100 trees, DTC. Okay, so we can use this class sklearn.ensemble random forest classifier here. And here, we can take it. So here we are taking it here. From sklearn.ensemble import random forest classifier, you have to take it. Only everything is same. Your files are same. There's nothing change here. The files you worked earlier, I had written a lot of code. I'm using those files only. I'm just adding few codes only into the previous written files. From sklearn.ensemble import random forest classifier or called it. Now I'm making the instance of it. Random forest classifier I'm using. And here, student, if I'm even not writing any number of estimators, nothing if I write it, you forget it. Suppose here, only I'm writing random forest classifier, that's all. Close it. You're not writing anything. So automatically it will take all the default parameters here. Number of estimator. Automatically it will be taking 100. So here, if you write random forest classifier 100, now 100 means number of decision tree classifier. Done. Even if you won't write, you make a random forest classifier, done, opening and closing bracket, do not write anything. Automatically, it will be working with the default 100 trees. Then here it is taking fit, prediction, and the matrix here will be taking. Means all the process is same, there's no change, but only internal working of the classifier which are coming into the ensemble, they will be working for the very heavy data sets to process them. That is there. Okay. If suppose, right now I'm getting this accuracy. If suppose, let's consider. Let's consider. Suppose I want to, suppose my accuracy is down. Let's consider. So in that case, now I can just change this number of classifier. I can change it to 150. Then again, rerun. We can check it out accuracy. Means the point is, this is one of the parameters you can keep increasing and you can stay at that number of trees where your accuracy is coming on to the highest accuracy, and you can just check it out your precision, recall also. If they are increased, so that is much better. Means your entire model performance, your F1 score, as well as your accuracy, you can check it and you can see your precision and recall. See here, everything is okay, na? They are on to the highest. So you can take that particular number of estimator here. Okay. If I'm taking 150, we are okay, then it's okay. You can take it 200, you can take it 250, that's all, or maximum 300. Do not give it a 500 or 600. Means here I say 100, 50, or you can give it a 50, 50, 100, 150, 200, 250, 300. In this way, you can do that. Okay. This one is a bagging. So only you have to call the algo. Everything is same. There's no change. There's one more. There's the extra trees. You can use the same extra trees if you want. Extra trees is only used whenever there is a huge data set. I'm talking about a very huge. In lakhs of your rows, lakhs of your columns are there. So they are, even random forest is not working. So you can go ahead with extra trees. Okay, so default also it is taking 100 decision trees internally, but it is being used only when there's a huge, I'm talking about a very enormous data set, not only normal here. DTC is homogeneous because decision tree we are taking means ensemble method. Ensemble method is taking all the trees decision tree classifier. All the 100 trees are decision tree classifier. That's why we say, because all the trees are same, which is a decision tree, we call it a homogeneous. Homogeneous means same type of classifier. No, it is predefined. The entire bagging has been done onto the decision tree. They are being done into the decision tree only. These are predefined return here. Okay. So this is one. So if we want to use extra trees, so we can take only this one, make the instance of it, fit prediction that you can do less like a normal one. So this one is a bagging. So bagging itself is a parallel technique. Parallel technique. Then there is a boosting. Boosting. In case of boosting classifier, this is another technique where the data set are being learned into the sequential order. So here we can take era boost. So here we are having one of the sklearn. class sklearn.ensemble add a boost classifier. Okay, so add a boost classifier is one of the algorithm which is learning the dataset in boosting order. Here, the number of estimators are basically 50 by default, and decision tree classifiers are learning it here. Okay, the data boost classifier is a meta estimator that begins by fitting a classifier on the original dataset, then fits additional copies of the classifier on the same dataset. But where the weights are incorrectly classified are adjusted such that subsequent classifier can be learned. So basically here, this data boost is used to enhance the learning. So here you can see, just a minute. Here you can see, we are using from sklearn.ensemble data boost classifier you can take. We are making the instance of it, fit, prediction, and the matrix we are going to use it. Students, everything is the same. There's no change. You have to use your old files. The files you had created earlier now, you just open those files and you need to run all, and then you add the code at the end of the file with this file. Okay, so add a boost classifier, by default what it does, there are certain parameters such as its base estimator. Base estimator means which algo is working. So that one is a decision tree classifier. Number of estimators are 50. 50 estimators are there. Learning rate is one of the parameters which are adjusting the internal weights of the model learning of the data set. Okay. And then rest of the process will be same. Means here, internal workings are different here. Okay, so this is there. Now, if we want to change the number of estimators, suppose we want to change the number of estimator. So here, suppose I had written 50 and you have to check out the results, what results are coming. If you want to improve the results, you can go ahead with 100. You can write here 150. You can write here 200. You can write here 250. Means you can keep on doing up and downs of this number of trees and check out here where your results are fitting the best one. So the point here. Okay. Okay. This is way. Now, certain times, now what happens? Suppose by default, what happens? By default, what happens? See, there is certain parameters working behind it. Suppose I say, let me take here data boost. Suppose I'm taking a data boost, and inside the data boost, suppose here, you see here, there is one of the parameter algorithm. Inside the algorithm, one word is given here, SAMME.R. This is one of the mathematical technique. Entire formulas are written here. So basically, you know what happens? This algorithm SMME.R. This is one of the mathematical certain mathematical formulas are working here. So there are two algorithms are working in behind of it. One is SAMME. One is SAMME. One is SAMME.R. These are two, and they work with a different classifiers. Okay, by default, suppose if I check by default algorithm SAMME.R is working. By default, it is working. So here estimator DTC is working automatically. Even we won't write any code. If I'm writing here data boost, I'm writing this only. That's all. I'm not changing anything. Only this one. I'm writing AD. That's all done. So everything is working as a default because estimator decision tree classifier is working with 50 decision tree algorithm. This one again, the mathematical calculations are being done in the backend. But at the same time, if I want to change this estimator DTC to any other algorithm, okay, if I want to change it SVC, that support vector classifier can work. So this algorithm we need to change. This value we need to change, else it will start throwing the error. It will ask to change it. So here what we can do, See here, ADA Boost by default algorithm SAMME.R is working because here the default here decision tree classifiers are working, but at the same time, if I want to change it with any other classifier name, so there we need to make a small change into the parameter, else it will start throwing the error or certain warnings. It won't allow to run the code. Suppose here I'm just calling support vector classifier. I'm using a support vector classifier. I'm changing, instead of DTC, I'm changing it to SVC. So here I'm using my base estimator. My model is support vector classifier. So here I need to change algorithm SAMME. Okay. Otherwise, what happens? This SVC has its internal kernel, which is having its value as a RBF field. Means there's a default value, either RBF or poly. So those values are settled with SAMME. So this we need to change it. Then only the code will run. And in case if I want to take here, suppose this one also linear, here it is working, then also I can work with this one here. So the point is here that whenever we are using a SVC, support vector classifier, so we need to change the algorithm SAMME.R, SAMME, and the default with the decision tree SAMME.R is working. Here it means these algorithms, certain parameters we need to tune by changing the algorithms name also. Now next, we are having another boosting classifier, which is a gradient boosting classifier. If I want to use it, simply I will call that from sklearn.ensemble gradient boosting classifier. Okay, so that is also there. Gradient boosting classifier it is. Okay, so this will be used here. So here I'm just calling from sklearn.ensemble gradient boosting classifier, making the instance fit training and the accuracy matrix we are checking it out. So all these are algorithm we use for the ensemble methods. But here, everything whichever classifiers we are taking, they are homogeneous. See here, basically everybody has to learn all these libraries. Yeah, you have to practice the code, you have to learn the libraries. To become a data scientist, you have to learn everything. All these things you have to remember. That is the only way. So all the codes you have to remember, all the library you have to remember. Is it okay, Manish? Right? Now let's learn to the voting classifier. What is this voting classifier all about? See, when we talk about bagging, boosting, they uses the homogeneous models. Homogeneous means all are DTC models. Now, certain time, if I need heterogeneous model, so here there's another classifier, that means a voting classifier. Voting classifier take all the models in heterogeneous mode. Heterogeneous means different models we are having. Like in Homo, we are having DTC only. In case of voting classifier, we are having different model, heterogeneous. How? You think it out. Suppose when we talk about the voting classifier, inside the voting classifier, here I can take, suppose, one of the model has a support vector classifier, one of the model has the decision tree classifier, one of the model has the KNN. You think it. We can make the combination of all these three different classifier. That's why we call it a hetero. Hetero means different models. And homo means same. Okay. So how this voting classifier works? Just wait here. Okay. When we talk about voting classifier, there are two methods: hard and soft. Hard voting it is KNN, the nearest neighbor, K nearest neighbor. We are having a hard voting and soft voting. We are having a hard voting and soft voting. Now, in voting classifier, you think, suppose I'm using a hard voting. Okay. Think out, suppose suppose I'm using a voting classifier. And my voting classifier is a heterogeneous classifier, which is having support vector classifier, decision tree, and KNN. So these three models are combined as a one. And my classifier has learned the data, any data I had passed to it. It has learned the data. Now here, when I'm giving the new data, whenever I'm passing a new data, let's take the very simple one, iris dataset. Inside the iris dataset, we are having 4 input features: petal length, petal width, sepal length, sepal width. And here, one needs to predict whether what is the species. Means here, if we are giving the new data of petal length, petal width, sepal length, and sepal width, so voting classifier has to predict what is this species belongs to. So here I can pass any values such as 6.2, 8.3, 7.8, 4.5. So here in species we are having Setosa, versicolor, virginica. Means 0 species, 1 species, or 2 species. So here I'm using a voting classifier. So classifier has to give that if these are the new value, what will be the answer among these? Setosa, versicolor, virginica. So here, if I'm using 3 models, suppose KNN, SVC, decision tree. Here comes the final results. So what will happen? This KNN starts predicting these values, petal length, petal width, sepal length, and sepal width. And based on its learning, it will say that these values belongs to 0. SVC says these values belongs to 2. Means it is virginica. Virginica. Here it is saying Setosa, virginica. Now DTC will start giving the response based on its learning. So here it will say this is 2. This is virginica. So here model will check it out where the highest votes are there. They are virginica are 2 members giving as an answer. So the final result will be 2. It means this petal length, sepal width belongs to 2 virginica. So this one is a hard voting. So this in voting classifier, it is a heterogeneous method. Heterogeneous method. Hetero means different models we are taking. Okay. So this is a case of hard voting method here. So you can see here, voting classifier is a machine learning model that trains on an ensemble of numerous models and predict an output based on their highest probability of chosen class as the output. It simply aggregates the finding of each classifier passed into voting classifier and predicts the output class based on the highest majority of voting. So wherever highest majority of voting is there, it will start responding to that particular output. The idea is instead of creating separate dedicated models, find the accuracy of each of them. We create a single model which trained by these models and predict output based on to its combined majority of voting. We are having 2 types of votings. Hard voting. In case of hard voting, the predicted output is a class of highest majority of the votes. Okay. So hard voting. So if I want to call the hard voting, from sklearn.ensemble, import voting classifier. Here I'm creating the different members. Here I'm creating the estimator blank list I'm creating. Now I'm appending this blank list with k-neighbors classifier, support vector classifier, decision tree classifier. And these are the instances I've created for the k-neighbors, support vector, and decision tree. They all are added into this list estimator. So 3 models start working. Which one? K-neighbors, support vector, and decision tree, heterogeneous model, hetero. Okay, that will start working. Now we will be using this estimator. Inside the estimator, my 3 models are present. The list is present with k-neighbors, support vector, and decision tree, and they will be used for voting classifier. So here, this is the same one which I had described to you right now. See here, only we need to call voting classifier. Here, there is one of the parameter estimators, means where is your heterogeneous models. So estimators I have created with KNN, support vector, and decision tree. Okay. So this estimator I had already created, that I am putting it here. And voting is equal to hard, I have to write it. Then fate prediction, we have to do it, and we need to check it out the accuracy. So accuracy is 1. So this one is a hard voting. Hard voting works on majority of votes. Now let's go to think out where you are having a you think of like you are having a soft voting. In case of soft voting, probabilities are given. Means here, if I'm using a soft voting, so here probabilities are given. Suppose here I'm using a classifier 1. Let's take a KNN. Classifier 2 as a support vector classifier, and this one as a decision tree. Let's take, or any other. So here, the model starts giving the probability of a particular class. You fill out, suppose here I'm giving any X input data. So here into the X input data, here I'm putting 4 different values of petal length, petal width, sepal length, and sepal width. So here, suppose here I'm writing 6.5, 7.8, 5.8, 4.5. So sepal length, sepal width, petal length, petal width. So here we need to predict whether the data belongs to 0 type, 1 type, or 2 type. So here now what will happen? Here the things will come with the probabilities only, chosen probabilities. Suppose here KNN says that these inputs belongs to class 1, that is 90%. 90%, this is Sitosa. This input is Sitosa. Classifier 2 says support vector classifier, that says only 10% it is Sitosa. Decision tree, which is a classifier 3, says only 1% this is a Sitosa. And the similar way, every classifier gave it self probability that this is Sitosa. Now here, what about the second? Means here this one is talking about the Sitosa. Now what about the versicular? In case of versicular, it is KNN is saying 8% it is versicular. SPC is saying 80% it is support vector. No, 80% it is versicular, 85% it is versicular. What about the Virginica? KNN is saying 2% it is Virginica. SVC is saying 10% is Virginica, 14% is Virginica. Now what will happen? The model, the soft voting will be making entire mean of entire class 1, mean of entire class 2, class 3, and find out the highest mean. So once it is making the average here, so here it is finding it out 65.6% probability is given to class 2. Class 2 means here it is versicular. Versicular. So it means this flower is versicular flower. So here with this input, the final prediction is class 2, it is a versicular. Okay, so here probabilities are there in case of soft voting. Okay, so here you can see voting classifier, estimator is equal to estimator. Here inside the estimator, your KNN, SVC, and TTC all are working, and voting is equal to soft I had made, then fit, prediction, and the accuracy I'm giving to it. So basically, voting is heterogeneous model, and backing and boosting is homogeneous model. Okay, read it down. Only algorithm changes are there. All the processes same. Internally, number of mathematical models are working. So the point is, your machine learning is working on the mathematical models. There are so many mathematical models. But we are having libraries. We do use the libraries directly. Is it okay now? Have you understood the technique? The technique is you can raise hand, that's all. Thank you for the responses. Thank you very much. So in this way, we can use the techniques. So you have to work onto a predefined files only. The files you had worked already, just open them, click on run all the file will be updated, and then add new things in the and also. So other algorithms you are ending on the same data set. These are ensembles. Now think out the situation. See, if I'm having a data set, I'm having input and the output. Inside the output, if I'm having, think out, you know, so here, you think out in this situation, we are having only one type of set, one type of values much, and here I'm having least value. Or if I change it, suppose I'm changing it to reverse. In the reverse, you think out, I'm having a Y. Inside the Y, I'm having only these values are higher side and only few values with a zero side. What does it mean? It means I'm having ample of data into the X, but my values are, one is very higher side, another is lower side. So such type of data set where I'm having these Y, where my data sets are not having equal values, we call it a unbalanced data set. Unbalanced data set. So though we can give a unbalanced data set, or you can call it a imbalanced also. Imbalanced data set. So my data is not balanced because all the values which are coming into Y, they are not equalized. We can give this data set to the model, but model will not learn more because we are having few values for one type and other types we are having much more. So we need to balance the entire data set. To balance the entire data set, there is one of the techniques, SMART technique. SMART is one of the techniques through which we can make the data set balanced. Okay, so remember, SMART is one of the techniques which will be making our imbalanced data set towards the balanced data set. So the point is, when we talk about these techniques, imbalanced data set. So here, certain synthetic rows are being created by the SMART technique here. Suppose here you think, I'm having some number of rows I'm having, and the data set is imbalanced. To take a situation. So here we are having certain input values. So input values, I can take it as the X1, X2, X3, X4, and the Y. So inside the Y, we can take it such as, let's take a value. I'm giving you so few values, 2.3, 2.1, 1.8, 7.8. And here, suppose I say the output is 0. Let's say. Now here it is, here I'm having 2.3, 2.1, 1.9, 7.2. The output is 0. 1.2, 3.2, 2.8, 8.2. Some values are there. So in 0, 0, we are having. And also I'm having, you think out where I'm having some values such as 6.8, 7.2, 4.5, 10.6. Let's take. I'm having only one sample. I'm making a general data set, assumption data set. So here, the point is, if I say I'm having 3 rows for 0, and I'm holding one row for this one. One row for this one. So how can I increase the number of rows in one, because these are least. Here I will say it is imbalanced because the number of rows for one are very least. If I want to make certain more rows, so certain synthetic samples are being created by the SMART technique. So SMART technique will be applied to make the data set balanced. Data set balancing it will do, and it will start creating certain synthetic techniques. So here what it will do, it will be making small change into the pre-existing value and make more rows here. Suppose this is 10.6, so here it will make a value just like 10.7. Rest of the values will be remain same. So these are the synthetic samples it will make, and it will create the value as a 1. Next one here, it will be creating such as 6.8, 7.2, 4.6. It is changed. Rest is 10.6, same earlier one, and it is 1. So in this way, now my data set is balanced. So synthetic samples are being created with the help of SMART so that the model can learn more and more here. Okay, so that is there. So here what we can do, we can take here, see here, SMART technique. So here, imbalanced data set could be created as a balance with the help of SMART technique. SMART technique is basically synthetic minority oversampling technique. In case of SMART technique, it is an oversampling method which will be creating the synthetic samples of the minority classes here. Okay, so here minority classes are making equal to the majority classes here. Okay, SMART does this by selecting similar records and altering the records one column at a time by a random amount within the difference of the neighboring records. So synthetic samples are being created here. So here I'm taking one of them here. Suppose here you say, I'm just loading all the files here. Okay. So here I'm randomly loading one of the data set, PMyIndianDiabetes.csv. Any data set we can load, any categorical data set, classification data set we can load. It could be any. So here I'm loading it here. Here I'm loading it. So basically I had given here, like I'm loading it. Header equals to true I had given, because what happened, generally this Be My Indian Diabetes dataset does not have here, here headings. Headings means what are the header names? They are separate. So here, if I want to write here the header names as the 0, 1, 2, 3. So here I'm giving make the heading 0 and give the new names with a range 0, 1. So 0, 1, 2, 3, 4 up to 7. Up to 7 here it is. So up to 7 it is being created here. Okay, so these are the data sets. So here you can see these are the Y. These are the Y. So these are the Y here. So we can see this data 0, 1, 0, 1 data only. Rest are X. So here into the 7th column here, I'm just loading the data set here inside the data frame. How many rows are there? You can just check it out here. The rows are 767 rows and 8 columns. 767 rows and 8 columns. That's all. Here, 767 rows, I'm loading. Now see here, I'm taking here data frame X is equal to df.ilog 0 to 7. So here I'm just loading input data. Here I'm loading the output data. This one is a output data. This one. 767. Okay. So what I'll do, total are 767. Now I have to check with the help of pandas function. That one is, I have to check the output value counts. Output value counts mean? Output value counts mean? What is the data frame y.value counts? 500. It means for the 0 type, there are 500 rows. For the 1 type, there are 267 rows. Means here, total are 767 rows. Total are 767 rows. And out of 767, 500 rows are 0 type. 267 rows are 1 type. So we have to, I will say in this case, the data set is imbalanced. Means it is not properly balanced. Even if I make the count plot of the out function here it shows the data set is imbalanced. It is zeros are higher, 1 is less. So what we can do, we can make the data set here balanced data set. So we can apply the SMART. SMART is one of the technique. SMART is one of the technique which I can use for installation. So you should know, like here what we can do. Here I just written this line just to check out the version, that's all. This is a way if I want to check out the version. So here I can write, what is my version? These are just, I'm showing you how to check out the version. Import sklearn or sklearn dot. If I want to check out the version, it is version. We can write this command. If I want to check out the version, so numpy dot version, numpy dot version. Just I'm randomly checking it. But here we need to make the SMART installation. How to make the SMART installation? SMART is an external library. We need to install it. So there you need to command pip install imbalanced-learn. Imbalanced-learn library we have to install. Done. It will take a time to install this library imbalanced-learn. So one can use any of here. This command, if you write it, that will work. Pip install imbalanced-learn. Your library will be installed after a certain time. You will be getting a message. Done. Once it is there, then you have to make this command markdown. Make this command as the markdown. Because second time you are not going to run this command because the library is installed now. Do not run this line once it is over. So installation process is done. Now you can call this mode. So even you can use this or this, but I'll suggest you use this. Both are okay. Here I had written underscore this one exclamation sign pip install. This one is nothing user. But here I'll suggest you take this command. This command you can take it and you write it and that will work. Installation process will be done automatically and you will be receiving a message. And then how you will be checking it out that once things are over now, installation process, if you give this line, okay, you're done, then you need to call this mod. So here you can call this mod from IMB learn. This is IMB. From IMB learn.oversampling, import mod. Mod is imported. Then you are making the instance of it. Inside this instance, you are sending smart.fit resample. You are sending it out the X and Y input and the output. Once it will make the synthetic sample, it will return you new samples. If you check it out, trainx.value count, these are there. So let's check it out more, that how many rows are being added. So what happened? If I take here, see now, if you check after this fit resample here, input I have sent and output I have sent. These are the returned values. So here, trainx.value count, these are the actual values, it is showing it here. And here, train y.value counts, here it is showing 500 rows for 0 and 500 rows for 1. Okay, so it is balanced now. It is balanced. So earlier 767 rows are there and now 1000 are there. So the point is your data set is balanced 500, 0, 501. So this is a smart technique. With the help of smart technique, we are making the data set balanced. If we are checking it out, the output here, SNS.count plot here, trained by, so here you can see 0 and 1 are equalized. And then here, once everything is settled down, here, you can use this new input and output, train X and train Y, you can use this test side, and this one you can use it. And you can use these one. Entire other things are the same here. You are making the modifications, everything you are going to do. Okay, so in this way, your smart are working. Okay, normal working you are going to do. Okay, now what I'm doing, I'm going to load one more file, iris.csv. Okay, let me check it out whether the data set is balanced or imbalanced. Students, see here, I loaded the file iris.csv. You can see this data. Students, give your response into query portal. You can tell me this file is balanced or imbalanced. Give me balanced. Only one word you have to give me. Balanced or imbalanced. You have to give me only one word. I'm waiting for your words. So this file is, I need more answers. Everyone I'm asking, just to write it here now. Okay, thank you for the responses. Thank you. So you are saying that data file is balanced data set. So I will say this file is balanced. Why it is balanced? Because 50, 50, 50. Total are 150 rows. So data equalization is there. Okay. 50 rows for, 50 rows for Setosa, 50 rows for versicolor, 50 rows for Pergenica. I'm loading one more file, wine_quality_rate.csv. So let me check it out. There's a quality factor. These are the value counts. Please tell me, this is a balanced data or imbalanced data? Give one word there. Give one word, balanced data or imbalanced data. Very good. Thanks for the responses. It means you had understood well. This one is a imbalanced data. So if we are having imbalanced data, we are segregating the data into X and Y. And here we can apply the SMART. To make the fit resample method, I can use it. I'm calling it here only. I'm making the instance, then fit resample input and output. Output here I'm making. So earlier, my total number of rows are 1599. But after making SMART, my total number of rows are 4086 because it is making different type of, because there are 5 to 6 qualities are there, 0, 1, 2, 3. So they are increasing all the number here. See this one. Students, this is a balanced or imbalanced? Can you tell me? If you answer, it means completely you had understood the topic well, all the topics well. You can answer me. This is a balanced or imbalanced after making the SMART. Now the data set is very good. The data set is always balanced here. So remember this technique. Yeah. The data set is balanced. So in this way, okay, Good. So here, the best way is the data set is balanced here. So the point is here, remember that whenever you are having a data set, so you can make those data set. If the data set are imbalanced, use smart, install smart, and call the smart and make the data set balanced. And then apply normal, any classifier you can get, normal processes, whatever you are doing it. Okay, shall I proceed now? Is it okay now? So this is overall for the like ensemble or smart to settle down the imbalanced data to the balanced data set. Let's understand hyperparameter tuning here. See, basically, currently now, like suppose we are having number of parameters. Means here, if I say, let's take any algorithm. Suppose here I'm taking lasso or ridge regression. So we one of the parameters such as alpha. So we need to test out its value such as 0.0001, or I'm testing out the value 0.01, or I'm testing out the value in this way. So what I'm doing, all the process I'm doing manually. If I say, suppose I'm using a support vector classifier and there I'm using a kernel. Inside the kernel, I'm having the values here. I can say RBF. Separately, I'm checking poly, I'm checking it out. And here I'm checking it out, the linear as well. But I'm doing all the processes very separate. So individual testing I'm doing. So there is one method here which I can use, and that method will find out that which particular value for the particular parameter is best. Okay, so that we can do that. So there is a process here, we call it a hyperparameter tuning. Hyperparameter tuning. When we do the hyperparameter tuning, it means the parameter could be tuned. Parameter means the parameter name and its different values could be tuned. So here parameter tuning can be done. So here we can do this hyperparameter with the help of grid search CV. Grid search CV. Grid search CV is one of the methods through which we can do the hyperparameter tuning. How we can do that? Whenever we are applying the grid search CV, we have to give here the model name. We can call this model as the estimator also. Estimator means simple word, model name. I need to give here parameter dictionary. Parameter dictionary here. Now, what is this parameter dictionary? Here I need to pass a dictionary parameter which is holding the value of the model parameter values. Means here, see, just wait. Suppose here I'm making any data set I'm having, I'm making a ridge. So here I'm making, let's say RD is the instance. Now I need to make a dictionary for the parametric value. So here I'm using param. Param is a variable. So here I need to create a dictionary. So here I'm going to create a dictionary. This will be passed into the parameter dictionary. So here I'm going to call alpha, means the parameter name. And here I can give different values I'm using. Different values I'm using. Okay. Now, here what I can do. I can make a grid search CV, and inside the grid search CV, here I can pass the model name. Inside the model name, I can give the RD. RD means this model name I have to give instance. And then here I need to supply a dictionary parameter here. Okay. Parameter here, I need to pass on where is the dictionary parameter. So here I need to supply this one, where my entire dictionary is there. That I need to give it. So here, parameter dictionary that I need to supply. I can make it as a GD. Then here I'm taking it a GD dot fit. Here I can pass on X, Y, input and output. So what grid search CV will do? Grid search CV will try to examine this particular model with each and every parameter. In alpha, it will start verifying alpha with 0.001 value, alpha with this value, alpha with this value, and goes on every value. So into the sequential order, this grid search CV will test out all the value. And after that, that will be giving you the best accuracy and best parameter it will be giving to you. Means here it will suggest that for a particular data set, which is a X and Y. So here, which particular values are working the best one with the higher results. And once I will be getting the value now, suppose here I'm getting a value, let's say I'm getting a value here. 0.001 is working best for alpha. So the same value I need to use. So after that, I'll take this value and I will be using this value here. RD, and here I will be using the same provided alpha value. Alpha is equal to 0.001. Done. Means here RD. it is rich. And now RD dot fit X train, Y train, then RD dot score, and other parameters, metrics, you can use it. So here we are testing it out each and every value. So grid search CV is one of the hyperparameter tuning method through which we can test it out each and every value, that which one is good. So grid search CV will take a lot of time to test out all the values with individual. All the given provided values are being tested it out, coming with the best result. The same is here. Suppose here I'm using, let's take decision tree. Here, I can use it. Here you can pass DTC. There is a parameter, which is a parametric list, because what happened in decision tree, there is one of the dictionary we have to create, criterion. So any parameter we can take it. Criterion is one of the parameter inside it, and the values goes with 2-3 values here. It's like Gini, entropy. I'll explain what are these later on. Gini, entropy. So I want to test out decision tree on a particular data set with Gini, criterion Gini or criterion entropy. So here I need to pass on GT. So here I need to pass this particular parameter here. So what DTC will do when I make a GT dot fit input and output, I'm going to give it. Here it is going to give it. Here it will test out first for Gini and then entropy. And then after that, it will be giving you the best parameter. That will suggest you that which one is the best parameter, Gini or entropy. Suppose here it says you are having Gini with score, suppose 98% you are getting with Gini parameter of criterion. So we'll be using the same into our code. So here we can use it. Same one here. Here I'm making a DTC decision tree classifier. Here I'm using, and here I'm making this one. Here I'm making using this criterion. Using here criterion is equal to Gini. I'll discuss more onto the Gini and entropy later on. Gini, got it. Then DTC dot fit extreme Y train. Then DTC dot predict. Then matrix. You have to check it out. So the point is here, grid search CV is a method where all the values are tested out. In a similar way, if I'm having a support vector classifier for the support vector classifier here also we are having certain parameter, such as here we need to create a dictionary. So here there is one of the parameters such as kernel. Inside the kernel, we are passing certain 3 values. We are having general 3 values. Linear, poly, RBF, these are the major one. And then here we can make. So we can call this grid search CV from sklearn.model selection. From there I can call it. Here I can give SVC model name. Here I can give this param. So here I will be giving this parameter. Okay. And then here. Then it will give the best result that would be taken into the actual one. So one by one, the testing will be done. So what will happen here? Here now, see, suppose we are taking a linear. Means here, what support vector will? Support vector will go first with linear, kernel linear, test out entire x and y onto the linear basis, find out the result. Then it will go with kernel poly, test out all the result, and then RBF. And then it will say linear is better, poly is better, or RBF is better, and here it will give the best parameters. After that, suppose here, I say, suppose here, there is one more parameter. Let's say, I say in support vector classifier, as we see, suppose here, I say kernel. Kernel is having 3 values. There are certain other parameters also. Suppose there is one of the C parameter, which is a kind of penalty parameter, which will be improved, which is reducing the error, improves the learning. So there are default values are present here, such as 1 or 10. Default values are there. Certain time it take 1 or 10. So here, suppose because there are a number of parameters here. So if we are using a grid search CV, so grid search CV do all the things into the sequential order. So here it will start taking the values. For support vector classifier, here it will take, then it will take this also. So what will happen when we are making here GD? Here we are taking it, input and output. Here. So what X will do, see, this data set will be tested out on linear, and it will check it out linear with C value 10, 1. Then it will find out its result. Then again, this entire data set on support vector classifier, it will be testing out linear with the value of 10. So sequential order, 1 by 1 testing it will do. Then next time, it will take these values to poly with 1, and then poly with 10 parameter. Means all the provided value, it will keep on testing, and it will take a time. Then RBF will be tested out with the value 1, then 10. Means 6 times it will make on testings. Then it will find it out the best one, and here it will say the best one is suppose RBF is coming with the C value 10, you use it. So this value will be used. So basically grid search CV is to I say time taking also, because it is testing it out all the values 1 by 1, so that we can do the okay. So all the testing process is being done here. So this one is a grid search CV. You can see it here. Hyperparameter tuning is there. Here I'm loading any data set. You can see it here, but here only the algorithms you can keep on applying here. So this one, Here I'm just calling from sklearn.model selection import grid search CV. I'm loading any data set. It could be any data set, not only. We are focusing on the methods. Here I'm making one of the variable as an alpha value, and here I'm giving the value of alpha. Different values here I'm giving of alpha that could be tested. Then here I'm making the instance model, ridge, and then calling this ridge here into the grid search CV model. So here RD is passed, and here there's one of the parameter that is a parameter grid, and inside it I have to send the dictionary value, and these dictionary values are alpha values. So here I had created a dictionary, and these alpha values are passed. Okay. And then what will happen after alpha values are passed? We are going to make the instance grid.fit, input and output will be taking it, and then we'll be checking out what the best score, what are the best estimator, what are the best parameters here. So here we can see alpha, these values are there. Okay, so suppose here it is just saying what is the best score. So best estimator dot alpha, best parameter. So we can check it out, the score has best parameter. So here it is saying alpha with this value, it is working the best one. This alpha values could be taken out. Then here we can take these values here. When we are working, we can take these values here. So you can see here, we are taking the same values. We are loading the data set. Here I'm going to use ridge here. The same values which are tested at the best one, this we are passing it here. And then normal process we are doing it. Okay. Say this one. Suppose here I'm using a decision tree classifier. I created a DTC. I loaded iris dataset. I created a grid parameter, which is a dictionary criterion. Inside criterion, I had passed two values, chain and entropy. And here I'm making the instance of it. So inside the estimator, I'm passing DTC. And inside the parameter, I'm just passing this variable where the entire dictionary is there for all the parameter and the value. These are the default settings. You give it or won't give it. These are the working. Means here it will be testing out the accuracy. Then here you're making the fit, making the instance, making the fit here for the input and the output. Then you can check it out the best parameter, best score as well. So here you can see criterion GNA 96% it is working. So we are getting criterion GNA is working 96%. So use this one here. While making decision tree classifier, use criterion is equal to GNA. The same here. If you see here, support vector classifier. So you can use here any of the method here. Suppose here. This one. So here you can see I'm calling from sklearn.model section import grid search CV. Dataset I'm loading, kernel with different values, and there is a C parameter with different values I'm passing. Even you can go to different models, find out the different parameters, making the instance of grid search CV, passing this one and passing this one also. Then fit here, I'm passing the X, Y. Okay. SVC, I'm using a SVC, support vector classifier, I'm using it here. Then here I'm just checking it out. Yeah, SVC I'm using. Then here I'm checking out CLF.best parameter. So here it is saying kernel with linear C1 values are being tested, the best one. So here this support vector classifier will check it out linear with C1 value, then linear with 10 value. Then it will check it out RBF with 1 and RBF with 10 values. Okay. And the parameter, which is the best one here, that kernel linear, C is equal to 1. The values which are suggested here, those values are being used here. Fit score, we are checking it out. Means the best value which is suggested, that will be used into the actual training and testing. So these are the grid search CV. These are for use for the hyperparameter tuning. Okay, where you can get the highest score. So this one is a grid search CV, but it will take a time. You know why? Because grid search CV will be taking out all the data in sequential order. But here, if you see, there is one more randomized search CV. In case of randomized search CV, it will never check any given parameters into sequential order. Never. But this is one of the alternative of grid search CV. That one is a randomized search CV. So here, entire process is same. Only library is different, randomized search CV. This one and this one I'll settle down. So, but now randomized search CV will not. Suppose here grid search CV is checked, so that will be checking it out each and every value in sequential order. But randomized search value will be taking out, suppose this randomly and give certain result. So, but it is taking a very less time because it will never take entire thing sequentially. Okay, so the best one is, I'll say, randomized search CV will not take any time, but grid search CV will take entire time. Okay, grid search CV will test out each and every passed parameter, but randomized search CV will pass any random values. It will just work on any random value, and that values could be tested. So it will not check with each and every value. Okay. Okay. So this is the last now. Yeah, tomorrow is a holiday. Tomorrow is Diwali here in India. So there is a holiday. Tomorrow is off. I feel you had received the messages also. Certain time what happens, Nana? There is just wait here. Whenever what happens, we are having a number of columns. Here I'm talking about a number of columns. I'm not talking about number of rows. I'm not talking about number of rows. I'm talking about, suppose there is a data set with number of columns. I'm not talking about number of rows. So here I'm having a column 1, column 2, column 3, column 4, column 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you can think it out. Suppose I'm having 50 to 60 columns with a normal number of rows. So whenever we are having a number of columns, but it's okay. Number of rows are okay. It's 300, 500, it's okay. So whenever we are having a number of columns only, so this situation, we can call it a curse of dimensionality. We call it a curse of dimensionality. Curse of dimension means here we are having number of columns. So what I can do, if I'm having only number of columns too much, means say 50, 60. So what I can do, I can drop certain columns. But if I drop certain columns from the data, it means I'm losing the data. So for that, I will not lose any data. So there is one of the technique, we call that technique as the PCA. Principal component analysis, where we can give that how many columns we are requiring. Means here, if I say, suppose I'm having 60 columns, I want to reduce down the total number of columns to 10. I want to reduce down the dimensions. I will not drop 50 columns. I will use the technique from sklearn.decomposition import PCA. And here we can select that how many number of columns I'm requiring. Number of columns will be given with one of the parameter. That one is number of component. Here I can select 10. So what this PCA will do, it will start finding it out all the highly correlated column internally and make them as a one column. So here, if I say, suppose this column number 1, column number 3, column number 7, column number 9, they are making, these 4 columns are highly correlated. So these columns mean could be find it out and create it as a one column. So 4 columns are merged into one. So here means out of suppose 15 columns, 4 columns are reduced and make it as the one. Next, suppose this one, this one, this one, this one. So here, these C4, C10, 12, and C15 columns are reduced to make it as the one. So this one is reduced to 1. So means here 8 columns are converted into 2. So with the help of PCA in the similar way, more correlated columns are find it out and make them as a 1. So means here their mean could be find it out. So here total number of columns could be reduced down to 10. So this we can do with the PCA technique, principal component analysis technique. So where we are having a number of columns, we can reduce down with the PCA, where the columns are not dropped, though they are merged as a 1 by finding out their mean value, by making them, by finding it out the highly correlated column together. So just a moment here. Just wait here. Just wait. I just stopped share right now. Let me find out one file case. Just wait, please. Okay. I had called PCA technique from sklearn.decomposition import PCA. I had loaded one of the data set, which is a Sonar CSV file. Inside this data set, we are having a 60 column. 60 columns are there. So let me tell you about this data set. This data set is relating with the Sonar's. Sonar means here, sea. Under the sea, submarines are moving, you know. Under the sea, submarines are moving. And whenever these submarines are moving into one direction, so they keep on sending the signals and they are receiving the signals back. With this, they are detecting what is the front coming object. This is a rock or a blast mine. So it means I'm having two things, R or M, rock or mine. So they send a signal, receive a signal. So there are 60 input columns are there. They send it and receive it back. And based on to that, here, this data set has whether the coming signal is giving me the indication of a rock or whether the coming signal is giving me the indication of mine. Okay, so sonar.csv file is there, submarine data set is there. So here I am just loading. Here, first of all, I had called the sklearn.decomposition import PCA. Sonar.csv, I had loaded it here. When I had loaded, you can see there are 60 columns are there. 0, 1, 2, 3, 4, 5, 6, and here, say this one. 207 rows, but 61 columns are there. You can see the last column here, M and R here, you can see here. M and R is there. M and R is there. Rock, mine. Rock, mine is there. Now I want to reduce down the number of columns from 60 to 10. So what I can do, instead of 60, higher I can call the PCA. So here I will be taking all the data from this 61 column as a X data. So here I had loaded the data, df.ilog 0 to -1. So 0 to -1, I had taken all the data into the X input data. And all the X data I had passed here into the PCA. So I'm just calling the PCA principal component analysis. I need number of components is one of the parameter where I can give how many columns, 10 columns. Here I'm saying I need 10 columns. So out from 60 to 10 you have to make. So here PCA will check it out, all the highly correlated column, make it as the 1. So here I'm calling this PCA.fit_transform, passing all the input data. And here I will be receiving this data, and this data is the same. I'm making it X. When I'm putting it here, I'm getting a 10 number of columns. And now this X will be the new input with a 10 number of columns. Okay. And then we can do scalar and standard scalar, we can do it, and logistic regression, we can do that. So basically here we are having PCA is one of the technique. PCA is one of the technique to reduce down the number of columns without dropping them. That's all for today. Thank you very much. Thanks. Tomorrow is a holiday. Tomorrow is off due to Diwali. Very happy Diwali. Very happy Diwali. Thank you. For the internship, you will be getting the information. Thank you. Thank you.